Woohoo! I am live. This is Math 40, Elementary Algebra. This is Chapter 7. Yay! Rational expressions. And we're going to be simplifying basically fancy fractions. So we're doing fancy fractions. So, irrational expression is an expression of the form a over b, where a and b are polynomials. That's why this comes after Chapter 6, which is all about polynomials. And b is not 0. Why can't b be equal to 0? That's a good question. And the thing is like if we have something like x over 0 or similar, that's undefined. Anything with 0 in the denominator is undefined. And in fact, it stays undefined until you get to almost graduate school. You have to be pretty far up before you start studying what to do, how to fix this. So unless you're committed to studying mathematics as a major or possibly as a very, really intense minor, you're going to be stuck in the world where zeros in the denominator are just not going to work. There's no way to fix it. So avoid 0 in the denominator like a plague. And because this is so important, we're going to have something we call restrictions. And we're going to warn people. We're going to say, hey, if you get this fraction, just don't let x be whatever. Don't let the value turn to 0 in the denominator. Okay, so having gotten that out of the way, let's start the real work of Chapter 7. First thing we're going to go through is something called opposite polynomials. Now, you might remember opposite numbers. Opposite numbers like 2 and -2 or -5 and 5, they're opposites if they have the opposite sign. Now, polynomials are a little more complicated because there's usually more than one term involved. So here I have x minus 5 and 5 minus x are called opposites because their terms are the same except with opposite signs. So let's look at x minus 5 is a positive x and a negative 5. And 5 minus x is a positive 5 and a negative x, or minus x, the minus in front of the x. So see how x here has a plus in front of it, has a minus over here. 5 has a minus, but it has a plus over here. As long as all the signs are completely reversed, they're opposite polynomials. So I've got 3 possible examples. And so my question for you is, which, if any, or maybe all of these are examples of opposite polynomials? So x minus 5 and x plus 5, are those opposites? You're right, it's no. Because it's plus x in both. So in other words, let me get my handy dandy, my highlighter. X stays x in both. So for them to be opposites, I would need a minus sign in front of the x in one of them so that they completely change signs. Okay, next up, B. The opposite of x plus 4, and then 4 minus x. That looks pretty good. I've got the plus in the middle here and the minus in the middle there. Are these opposite polynomials? And hopefully you said no. Why is that? The opposite of x plus 4. Notice the x has the minus, the 4 has the plus. I just changed the order. 4 minus x is positive 4 minus x. Notice the x is minus in both, and the 4 is the same. In fact, these two expressions are actually equivalent. These are the same. Those two have the same value. Positive 4, negative x, or the opposite of x. Positive 4, the opposite of x. So they're not even opposites. They're the same. So this one's another no. Now, what about this one? X squared minus 3x and 3x minus x squared. You got it. This one is, that's the real deal. Yay! So it's a no, and a yes. Awesome. So why do we care? Well, here's the cool thing. If we have opposite polynomials in a fraction together, so 1 minus x over x minus 1, those are opposite polynomials. If we change the order completely like that, we can cancel them and end up with a -1, which makes things a lot easier. Woohoo? Woohoo. Okay, so let's go on. Let's do another page of this. The second page, we're going to look at restrictions. So one of the important things to be looking out for when we're dealing with fractions is when the fractions are going to explode. So what sort of warnings do we have to include with them? For example, if I have 1 over x, what do I have to worry about? Well, with fractions, the big thing you have to worry about is the denominator can't equal 0. And here's the thing. There are a couple ways to do this. If I want to find the elephants to make sure no elephants come in, I could say you can let in all the animals except the elephants, or you can find the elephants and just say don't let them in. And so that's what I'm going to do here. I don't want to let the denominator equal 0, so I'm going to set the denominator, set it equal to 0 to find out when it equals 0, and then I'm going to say don't do that, whatever that is. So I'm going to set x equal to 0. X equal to 0 is bad. So I'm going to say don't let x equal 0. Does that make sense? So don't let x equal 0 right here. So find all values of x for which the rational expression is undefined. It's undefined for x equals 0. Okay. X minus 1, I'm going to set that equal to 0, right? There's the denominator. X minus 1, set it equal to 0. Add 1. I get x equals 1. So my answer here, it's undefined for x equals 1. So that's the answer I'm going to give them. If I were giving it as a present to somebody, I would say don't let x equal 1. Now, I can do some pretty sneaky things. For example, I could give you a lot and complicate things a lot and ask you, okay, what are we going to do with this one? And you'll be like, oh, there's so much going on. Nope. Just look at the denominator. X squared minus 1. Look at when it equals 0. Okay. Now, do you remember how to factor this from the polynomial section? X squared minus 1, it's a difference of 2 squares. I get x plus 1, x minus 1. So when is this actually equal to 0? Either when x plus 1 equals 0 or when x minus 1 equals 0. X equals -1 or x equals +1. So my two values, it's undefined for x equals -1 and +1. Those are the two numbers that make the denominator 0. Okay. Now, what if I try to be fancy? And I'm like, what if I put x plus 2 on the top? You're going to say, no, it's the same denominator. If it's the same denominator, it's the same answer. X is the whole expression is undefined when x equals 1 or -1. One of my puppets was trying to get on the screen. Okay, how about this last one? x squared plus 1 equals 0. Well, I'll tell you something that happens. So let's take a really close look at this. X squared is at least 0. Why do I say that? Well, when x is 0, x squared is 0. But when x is anything other than 0, x squared is positive. If x is like 1 or 2, x squared is like 1 or 4. If x is negative, x squared is positive. So this part is going to start off at least 0, and then we're going to add 1. Can we get to 0 by adding 1 to something that's already at 0? And the answer is there's no solution here, depending on how the WebAssign wants, or this is the denominator cannot be 0, or possibly the rational expression, or the rational expression is always defined. So in other words, this denominator, because it starts out at x squared and then you add 1, means it's never going to be 0. It's always going to be at least 1 or more. So you don't have to worry about this one at all. But I'm not sure what WebAssign wants. So, and if none of these work, text me and we'll figure it out together. Okay, I'm looking at the next page. You know what? Let's throw caution to the wind. We're only at 12 minutes. I bet I've got 3 more problems I want to do. I bet we could get through these. So let's give them a try. So this problem is asking us to simplify. Assume the denominator is not equal to 0. So now that we've already said, okay, we know when the denominator is equal to 0, like for example here, when would the denominator be 0? The denominator is 3x. What would make that equal to 0? You're right, x equals 0. So this would be, we'd say don't let x equal 0. But what they're saying in the problem is they're like, you know what, don't sweat it. We already worked on that. Now let's get into the next step. And the next step is, let me start up above it and say, if I gave you a fraction and I said the fraction was 3/6, would you feel comfortable with that? And hopefully you would say, ooh, we can reduce that, right? You can actually cancel the 3 and the 6 and rewrite it as 1/2. And that's reduced, right? That's what we're going to do with these expressions. With these rational expressions, we're going to try to reduce. And so there are a lot of styles for doing this. My style always starts off with rewrite the problem. And then I'm going to take a look here, and I'm going to see that I've got 3xx all over 3x. And I'm going to realize, wait a minute, the 3's cancel. And one of the x's cancels. And I end up with an x on top. And if everything's gone on the bottom, what's left? You're right, it's 1s. And x over 1 is just x. So we're just going to start reducing. We're going to start canceling. This is a lot like what we were doing with exponents. Okay. Next up, what if I have 3x over 3x squared in the denominator? Now, you could ask, do we have to write this out like this? Couldn't we work in with it here? Absolutely, you can work here. I just like it like this because I see it. I think it's easier to work with. But you can do it however you like. Again, everything cancels, but that lone x that's down here. Should probably circle this one up there. But what's left on top? You got it. It's a couple of 1s. 1 times 1 is 1. So 1 over x is our answer. Woohoo! So we're reducing fractions, but now we're reducing them when we have variables involved. Okay, last one for this video, and then we'll take a break and then go on to the next video. Okay, this is getting a little more complicated. I've got 3x, x, y, z up on top. Take a look, confirm that you agree. 3x, x, y, z. And then down the bottom, I've got 3x, y, y. Okay, let's talk about what cancels. 3, yay! An x, yay! A y, yay! And that's it. So I've got an x and a z up here and a y on the bottom. So I think I've got xz over y. What do you guys think? Awesome. So one note about this. If I were to give a restriction for this, if I gave you, I would say, well, this fraction reduces to xz over y. And I would say, don't let y be 0. And you'd say, well, of course, because this is in the denominator. And I'd say, don't let x be 0. And you'd be like, what? And the reason for that is back here in the original form, x can't be 0. See how it's in the denominator? So it can't be 0 like that. And if your great-grandmother can't be 0, it passes down to you, even if you're not the same. Even if you don't have an x in the denominator, if your great-grandmother had an x in the denominator, that's all it counts. So we would say don't let y equal 0 and don't let x equal 0, weirdly enough, because we remember where it came from. Woohoo? Woohoo. Okay. Next video, we're going to continue with some simplification and then do some interesting things with, I believe, if I'm correct, we're going to do some really interesting things with some measurement. Woohoo. Okay. Math on, guys. I'll see you in the next video. Woohoo.
To use a slightly cruder